This question has been asked in GATE 2013. I will read it out for you. A scheduling algorithm assigns priority proportional to the waiting time of a process. This means longer a process waits, higher will be its priority. Every process starts with priority 0. The scheduler reevaluates the process priority every t time units and decides the next process to schedule. If you can recollect the round-robin scheduling algorithm, then you would understand that this is similar to the time slice. Next, they're telling us which one of the following is true if processes have no input-output operations and all arrive at time 0. So having no input-output operations makes things a lot simpler because the processes will only be competing for the CPU. Now what happens is we can make out that this is very similar to round-robin scheduling. Why? Because as the scheduler reevaluates the process priority, the currently executing process may have lower priority than a waiting process. Now this may cause preemption of the process which is executing on the CPU. So we can make out that the given scheduling algorithm is equivalent to round robin. Also, the options that are given to us come nowhere near to the scenario that is described. See, they've given us it is equivalent to FCFS. Now FCFS is essentially a non-preemptive scheduling algorithm, but we can clearly understand by reading the question that preemption will take place now and then. So FCFS cannot be the right option. What about SJF? SJF is another non-preemptive scheduling algorithm, so it is rejected given the same reason as FCFS. And what about SRTF? Now SRTF is the preemptive version of SJF, but nowhere in the question has it been mentioned that the scheduling algorithm is scheduling processes based on their burst time. So SRTF cannot be the right answer either. So the correct answer has to be round-robin scheduling. But let's not settle for this. Let's verify the claim that we have made with the help of an example. Okay, so let's see this. So I'll take up an example. So let's say I have 3 processes, P1, P2 and P3. The arrival time as it is given to us is all zeros. I'm assuming the burst times to be 2, 6 and 8 respectively. Now all processes start with a priority of 0. Okay, the priority of all processes is the same, so 0, and it is supposed to be the lowest priority. Obviously it has been mentioned that greater the waiting time of the process, higher will be its priority. Initially no process is waiting, right? It is yet to enter or it is yet to start competing with the CPU. So no process is waiting and all have the same priority of 0. Now let's see how the scheduling will take place. Now initially what happens is, since all processes have the same priority and the arrival time is also the same, the tiebreaker has to be the process number. That means the process with the smaller ID will get scheduled first. So we have no other choice but to schedule process P1. See, P1, P2, P3 all have the same priority and their arrival times is also the same. So I have to use the process number as the tiebreaker. Now if process P1 gets scheduled at time unit 0, then till what point will it use the CPU? It will use the CPU for t time unit. See, it's been mentioned that the scheduler reevaluates the process priority every t time units. Now this t value has not been given to us. Let us assume that the value of t is 2 units. So what will the scheduler do? The scheduler will reevaluate the process priority every 2 units. Now process P1 has executed for 2 units and coincidentally its burst time was 2 units as well. So process P1 has finished execution and has left the system. But since process P2 and process P3 has been waiting, their priority will increase by 2 units each. So now process P2 and P3 both have the same priority, but their arrival times also happen to be the same. So once again, I'll use the process number as the tiebreaker. Now, process P2 will get scheduled next. For how many units? For T units, because after T units, the scheduler will reevaluate the priorities. So since P3 was waiting for 2 units, its priority is increased by 2. Now, out of the 2 processes in contention, process P3 has higher priority. So process P3 will now get scheduled. The CPU is preempted, or the process gets preempted from the CPU. P2 gets preempted from the CPU and P3 takes over. For how many units? For 2 units, right? Now, due to this burst, due to this time of 4 to 6, P2's priority has increased by 2 as well, because in this time 4 to 6, P2 has been waiting for the CPU. So now we find that P2 and P3 have the same priority. So once again, the process number acts as the tiebreaker and P2 gets scheduled once again. So in this way, the processes will get hold of the CPU and relinquish it every T units, right? So this is same as the round robin scheduling known to us, right? Because indeed T is acting as the time quantum in round robin, because the priority of processes is being reevaluated every T units, and preemption of currently executing process is also occurring just like it happens in round robin. A process is preempted once its time quantum expires. Thus the given algorithm is equivalent to round robin. So I hope this helps. Thank you.